Now we're going to look at in some detail at the confidence set for the slope and the intercept, the joint confidence set for the slope and the intercept. So we start with basic data, x's and y's, pairs of x and y's, and we fit a line through these the way we've done so many times before, and the output from this typical regression will result in a slope, the slope of this line, and it will result in an intercept, which is the point on the y-axis for x equal to 0. So this corresponds to a single point, an alpha, an estimate of alpha and beta in the plane. And we derived the formulas for this, the confidence set, which is an ellipse in the plane. It's a set of all alpha-beta pairs such that the estimate of the pairs in this context differ by less than this f from the estimates. And you can expand this by inserting the alpha hat beta hat here and the alpha beta here, and expand this into a quadratic equation, and that will give you a set of values which will look something like this around the point estimate. So that's the confidence ellipse, and now we would like to draw conclusions based on this, make some inference, and that would be typically something more than just saying that the alpha and the beta are inside the ellipse. We'd want to draw conclusions about the intercept and the slope, but they have to be simultaneous. So we want to make inference on both of them at the same time. And to do that, we can simply figure out what's the maximum and minimum value of the intercept within the set. And we obtain a bound on the intercept in this way, and then correspondingly bounds on the slope in the same way. Now look at this. What we've done is we've said that we have a 95% confidence set for the slope and the intercept pairs, all possible pairs that satisfy the inequality. And within that set, the intercept never goes below this bound, never above this bound, and correspondingly the slope is between these two bounds. The thing is that this is going to be conservative because there's much more space between these two bounds than there is inside the confidence ellipse itself. But however, we do know that we have at least a 95% probability of simultaneously covering both the slope and the intercept with this method, which is different from when we look at the regular confidence bounds, the T confidence bounds for the slope and the intercept. So if we do that, we only take the usual standard error times a T in each direction, which is these finer dotted lines. And when we do that, we obtain obviously narrower confidence intervals, but they're only valid for one at a time. So you have a confidence bound now for the intercept alone or for the slope alone, but the simultaneous coverage confidence is not 95% anymore. It's going to be less because each one of these bands here has 95% confidence coverage probability, if you like, or confidence, and correspondingly this band here has a 95% coverage probability as you repeat these experiments over and over again, but the intersection therefore must have less than 95% confidence. So that's the relationship between the Scheffe confidence bands, if you like, which is these outer ones, which are based on Scheffe's ellipse, and the regular T-valued, T-based confidence sets, which only work for one at a time. And the formulas themselves are the usual T that you get out of the summary command in R, or the confidence set which you need to put more work into deriving yourself, used on a based on the number of comparisons, which is 2 in this case, and an F distribution based on 2 degrees of freedom in the numerator and n minus 2 in this case for the denominator.